Okay, this lecture is about molecular potential energy surfaces. This is really just a very short introduction to the topic. Of course, this is really a many-body quantum problem, quite a complex problem, where you have to deal with electrons, you have to deal with atoms, and you have to deal with the time dependence of both. In practice, we're going to make many approximations. Usually when we run molecular simulations or rare events methods, we're using the Born-Oppenheimer approximation. And the Born-Oppenheimer approximation actually begins with the adiabatic approximation. That a system in eigenstate K, if exposed to a gradually imposed perturbation, remains in eigenstate K if that eigenstate is in a spectral gap. That is to say, if the energy levels are locally separated in the energy spectrum. Now, how gradual that perturbation needs to be in order for this to be true depends on the size of the energy gap. Now, the Born-Oppenheimer approximation says that for all practical purposes, the nuclei are very slow and that the electronic state responds instantaneously to changes in the positions of the nuclei. So these two things are decoupled because the nuclei are about 2,000 times heavier or more than the electrons, and therefore the nuclei should be a square root of 2,000 times slower than the electrons. So if we were solving the many-body problem with the electrons and the nuclei and the time dependence all together, then we would have a Schrodinger equation that looks like this. And this Hamiltonian would include absolutely everything. And we can imagine now separating this problem into a static, time-independent electronic structure problem. And that looks like this, a Hamiltonian that just deals with the electronic parts. This is the kinetic energy of the electrons, the nucleus-electron interactions, and the electron-electron interactions, acting on a wave function in which the positions of the nuclei are given parameters, fixed set positions, and the electronic state is the unknowns, the molecular orbitals basically we're solving for here. Then you have a eigenfunction of this problem that inherits the dependence on the positions of those nuclei. So this is basically the electronic problem, and you could make an entire course on this particular subject, and most of the time in this course what we'll be talking about is using things like density functional theory and rather simple versions of electronic structure theory. Now, once you have at any given position, the ability to find the ground state potential energy, then we're going to add to that electronic energy the repulsion between the nuclei and the kinetic energy of the nuclei. And that gives us a new effective operator that describes the evolution of the nuclei. And now we can solve the separate nuclear problem. So this is now a Schrodinger equation that describes time-dependent quantum nuclei evolving according to this Hamiltonian. As I mentioned, there's a lot of approximations that go into just solving the electronic structure problem itself. Many additional approximations along the way that I won't discuss here. But the dynamics of the nuclei, we typically go ahead and just assume that they are classical. And there will be cases where we have to make corrections for that, particularly for proton transfers and things. But for the most part, we can use Hamilton's equations of motion, take this nuclear Hamiltonian, and just use Hamilton's equations of motion to solve for the evolution of. Now, the potential that we get out of this, let's go back and look at that. So we take that electronic problem, we add to it the nucleus-nucleus repulsion, and that becomes this Born-Oppenheimer potential. So that potential is the one that we'll talk about in most of this course. It is a function of 3 n variables, an incredibly complicated object itself, even though we've made several approximations. And even if you look, for example, at the reaction A plus BC, going to AB plus C. This is a simple atom exchange reaction. Already you're dealing with 9 dimensions. And to put that in perspective, we're all familiar with these one-dimensional potential amine force kind of curves, for example, a Lennard-Jones potential. And it's very easy to describe what that is by setting out a grid, right? I can compute points along this distance axis, and in 1D it's no problem. I can basically make a table to describe this function to arbitrary precision. But if I wanted to do the same thing to describe a 9-dimensional potential energy surface, say with 10 points associated with each dimension, then I would need 10 to the 9 points, right? So 10 to the 9 DFT calculations is a tall order. Really, even for 3D, it's already way too many calculations to be manageable. Okay, so how do we make progress? Well, there are 3 tricks that really allow us to do some useful things with computation. One is that we can switch to internal coordinates, and we can choose those coordinates very carefully so that we get rid of a lot of external degrees of freedom. To always take advantage of the indistinguishability. There are a lot of times symmetry operations that allow us to only compute a part of the landscape and infer what it should be from symmetry for the rest of the landscape. Indistinguishability is really just one kind of symmetry, but in many cases there are additional ones. The last thing that we can take advantage of is the use of collective variables. And we really won't get to this until later parts of the course. Right now we're going to talk about all atom descriptions of the potential energy landscape. But as we go on, we'll talk about collective variables, we'll talk about projections, and we'll talk about free energy surfaces. And say one last thing about linear versus bent geometries. So if you have a linear molecule, A, B, C, and we count its degrees of freedom, here we have 3 center of mass translations, we have 2 rotations, we have 2 bending modes, those are both degenerate, and then we have 2 bond stretches. Now, as that molecule becomes bent, there are 3 center of mass translations, same as we had before, there are 3 rotations, there's 1 bond vibration, and there are 2 bond stretches. And so what has happened here is that 2 of the bending modes that were degenerate became an extra rotational mode. All right, so let's say a little bit about atom exchange reactions now. This is a big topic in collision theory, and I have not made a video about collision theory. The reason is that I really want to focus on high-pressure gas reactions and also reactions in condensed phases. Collision theory is extremely important for reactions in the gas phase. It was the beginning of predictive rate theories. At least it was able to predict prefactors. But it doesn't really predict the fraction of the trajectories that will result in a collision. That is sort of information that you have to separately put in by thinking about a more detailed consideration of the potential energy surface or the quantum scattering matrix. And that area has been really beautifully laid out in the book by Raphael de Levine. So I'm going to move on past collision theory and cross-sections and go straight to talking about this very simple reaction, H2 plus H, that goes to H plus H2. So all that's happened here is a hydrogen exchange. This is a reaction with a fairly low barrier. You can actually study this experimentally by monitoring the fraction of para-hydrogen in an ortho-para mixture. We can even make this one step simpler by going from the 9-dimensional potential energy surface to a case where we're collinear. And now there are only 2 internal degrees of freedom. If it's collinear, there's no bonding angle. The potential energy surface, in terms of these variables R1 and R2, the bond distances between the first and second and third hydrogens. This is showing these 2 axes. If you follow this channel out to infinity, you get to the reference energy as 0. Also, if you go in the vertical direction here, you get to 0. And right around the transition state here, the saddle point on this energy landscape is between 0.3 and 0.5 eV. And if you move along the diagonal here, then all atoms are getting far apart, and that will take you to a very high energy of several eV. So I've shown here a trajectory depicted in green that would look something like this. I've also shown that trajectory in another form here. This is R1 and R2 versus T. Now these things are oscillating down here as along the flat part of these trajectories. This is R2 versus time is oscillating, and then it starts to take off and rise. Here, R1 is getting smaller, and eventually it comes down, it forms a bond, and it starts to oscillate. So what you're seeing here, this is the vibration of the stable product molecule, and this is the vibration of the reactant molecule. And over here, you also see these vibrations. Now, one of the things that you might notice here is that this does not look like the path that a marble would take on this energy landscape. This is an analogy that people make a lot of times, but actually that's only true if you choose very special coordinate systems that make the kinetic energy operator diagonal. Okay, so what's happening here is that oscillations in R1, if I make R1 longer, it tends to make R2 shorter. And so you see that reflected in that the oscillations here aren't perpendicular to the direction of the channel. If we were to try to write down the Hamiltonian in terms of variables R1 and R2, which are coupled to each other, changing the length of one tends to change the length of the other one, then we would get a rather complicated kinetic energy term in the Hamiltonian. So this looks like the velocity along BC and RAB in a linear combination with each other, and then you square that, and that's going to lead to all these cross terms that involve the velocities of both components. So that if you run trajectories with this Hamiltonian, you would see these curves that don't really look the way you'd imagine a marble rolling around on this landscape. Now, the way to get rid of this problem is to diagonalize the kinetic energy operator. This is going to lead to a more complicated potential energy surface, but it allows us to do a lot of things that are actually quite important, and we'll talk about that in a minute. When you don't have this diagonal kinetic energy operator, your dynamics do not follow a very simple separable equation in which all of the variables evolve according to the forces on those variables. So what you do is this Jacobi transformation. We're not going to do a lot of this. I'm just going to walk you through what one of them looks like. This is the transformation for a atom exchange reaction with 3 atoms. You have coordinate x and a coordinate y. Y corresponds to the distance between the BC bond, and x corresponds to the distance between A and the center of mass, the BC fragment. Now, you can scale these coordinates x and y and get new coordinates RAB plus gamma as an undetermined constant times RBC, and Q2 is just a scaled version of the BC bond length. And now we can determine these two constants, gamma and epsilon, so that you diagonalize that kinetic energy operator. And so what does a diagonalized kinetic energy operator look like? Well, notice that you have the two velocities, Q1 and Q2, both appear like regular, as though they were Cartesian variables. You have and you have a single mass that's associated, same mass associated with both of them. So this is a particularly convenient form of a diagonalized kinetic energy operator, that you have one mass for both. And this is the potential energy surface. Now, this potential energy surface is now somewhat more complicated than we had before. Before we had this very intuitive RAB and RBC arguments, and now we have to invert the relationship here and then use those to get my U function. So the lines of constant RAB are no longer at perpendicular directions to the RBC. So when we do this diagonalization, we end up with a new set of coordinates that makes a skew angle in the RAB and RBC constant lines, right? So remember that RAB constant and RBC constant correspond roughly to the characteristic bond lengths of the products and the reactants, diatomic molecules that are formed. So that skew angle between those is this angle phi, and it's defined in terms of the masses of the atoms. Now what happens with this mass ratio is that if you have a heavy atom being transferred between relatively light atomic centers, then that skew angle is about 90 degrees, and you recover a picture that doesn't look so much different than the one that we naively wrote down before. But if the atom being transferred is relatively light compared to the A and C molecules on the outer edges, as in this case, this chlorine and chlorine transferring a hydrogen atom, the hydrogen atom being the very light atom, then that skew angle becomes very small. And now the diagram starts to look like this. Now when you plot the dynamics of a trajectory on this surface, it looks exactly the way it should if it was a point particle moving according to these forces, with each direction being sort of an independent direction in the equations of motion, right? So recall that what we were after is to be able to write down something like this, where each degree of freedom is associated with a mass and evolves according to the force on itself. Okay, so that's the effect of doing this coordinate transformation. You get a relatively simple and intuitive framework for the dynamics. Now, why do we care if our dynamics have this property? Well, it's a lot easier to construct dividing surfaces with coordinates that look like this. We can use the fact that the coordinates are locally separable from each other and count on the validity of the transition state theory assumption then for at least short distances. We can also begin to separate the coordinates and develop one-dimensional tunneling corrections that will work reasonably well in many cases, right? So the only way that you can take advantage of the separability property to do both of these things is to get a diagonal kinetic energy operator. Now, the problem is, of course, that these Jacobi transformations are hard, and so we would like to have an easier way of doing things, and fortunately there is a way of doing that, at least locally. You know, the Jacobi transformation has the advantage that it becomes separable everywhere. But what we can do locally is we can come up with something in a harmonic approximation based on mass-weighted Cartesian coordinates that will allow us to do a very similar thing. And I think I will stop there.